Je vais changer en anglais en réponse. Okay, so good afternoon to everyone. First of all, I would like to thank the organizers for the invitation and really apologize for not being there physically, but due to the train strike and other constraints, it was quite hard to attend, so sorry about that. Today's presentation is about energy quality time optimized mapping for imprecise computation tasks on multicores. And this is a work that has been done with a previous postdoc in the team called Lemo. So here's the outline of the presentation. We will start with a description of the target domain and our problem understudy. Then I will briefly summarize the state of the art and the main contributions. Then we will go to the proposed problem formulation as a mixed integer nonlinear programming and how we transform that to a mixed integer linear programming. Then we will discuss about our optimal and heuristic decomposition-based algorithmic solutions that we have used. Briefly, we will go to some representative results to evaluate these methods. And at the end, we will conclude and discuss a bit about the extensions of this work. So our target domain, we are focusing on multiple architectures. They have several processing elements. Thus, they're able to execute many applications at the same time. And we assume also that our architectures have dynamic voltage and frequency scaling capabilities, in the sense that each core can have its own voltage and frequency. Now, regarding the target domain for the applications, we are focused on applications that accept approximate results as long as a basic quality of service is satisfied and they're having deadlines. So these kind of applications we can find in multimedia, target tracking, real-time heuristic search, and control systems. So in our problem understudy, we consider that the applications can be modeled using the imprecise computation task model. So as you can see on the left in the figure, this task model allows us to split a task into a mandatory subtask and an optional subtask. So the mandatory subtask, it is there in order to have the required basic quality of service, and it should be always executed. On the other hand, we have the optional subtask, which has as goal to enhance the quality of service of the application. And in this work, we consider that the quality of service is a linear function of the execution cycles of the optional subtask. Thus, the more execution cycles we have for the optional subtask, the higher is the quality of service. So our problem understudy comes on how to decide the mapping of the imprecise computation tasks on this multicore platform with the goal of maximizing the quality of service, subject to two main constraints. The first one is the energy supply, and the second one is the real time. So regarding the energy supply, this is given by an upper bound in the energy consumption that our system is assumed to have within a given period. And the real-time constraint implies that both the mandatory and the optional subtask should be executed before the deadline of our task. So now we need to decide three main points. The first one is the task allocation. Then we have the optional subtask adjustment and the frequency assignment. Regarding the task allocation, this is to decide which core will execute which task. For the optional subtask adjustment is to decide how many execution cycles we will allow for the optional subtask. And last, for the frequency assignment, is to decide with which frequency we will execute finally our task. So I'll go a bit briefly in the state of the art regarding the task mapping problem. Mainly, we can have two categories. So the first one is the energy-aware real-time task mapping. There, we have usually as goal to minimize the energy consumption, assuming resource or timing constraints. The majority of these approaches are focusing on precise computation task models. Thus, we have only mandatory tasks. The other category is the quality of service aware real-time task mapping. So here, mainly the goal is to maximize the QoS subject to energy and or resource and or timing constraints. So here, the majority of approaches focus on the imprecise computational task model. So our work clearly belongs to the second category. Now, if I go a bit in more details on what happens with the state-of-the-art regarding the QoS-aware real-time imprecise computation task mapping, we can classify the approaches based on what we can see in this slide. So actually, we have what types of decision variables are taken into account. Do they check the frequency to task assignment? Do they decide the task to process allocation? And do they decide the task adjustment? Then regarding the objective, is it only maximizing the QoS, or it is also minimizing the energy consumption? Again, regarding the constraints, do they take into account a real-time execution, and do they take into account the energy consumption? And at the end is whether the solutions are optimal or heuristic. So here we have some approaches that focus on platforms that they do not consider dynamic voltage and frequency scaling. So that means that the decision variable regarding the frequency to task assignment is omitted from the optimization problem. Then there are other methods that do take DVFS into account, but they're simplifying the problem, either because they are focusing on single core platforms, or they assume that the task to process allocation is fixed and given in advance. So in this case, the task to process allocation decision variable is excluded from the problem formulation. We have also some works that they have a double objective, that is maximize QoS and minimize energy consumption. And overall, we can say that the majority of existing works are focusing on designing heuristics. However, it will be interesting also to have the optimal solution. So in this way, we can check how far away a heuristic is from the optimal solution, and thus, in this way, we can improve our heuristic methods. So in this context, we are focusing on a joint design optimization problem, where we take into account the frequency to task assignment, the task to process allocation, and the optional subtask adjustment. And we are providing optimal and heuristic solutions. So this is a summary of the contributions that we have. As a first step, we have the formulation of our joint problem, taking into account DVFS and task mapping. And this problem is formulated as an MINLP, so a mixed integer nonlinear programming, that optimizes concurrently the frequency to task assignment, the task allocation, and the suboptimal task adjustment. And our goal, as we said, is to maximize the QoS under these two constraints, that is the energy supply and the real time. So then we have proposed a problem linearization in order to safely transform the mixed integer nonlinear programming to a mixed integer linear programming that has the same feasible region, so we are not losing performance. And this is achieved by linearizing the nonlinear items in the formulation. And how we do that? That we do with adding auxiliary variables and linear constraints. Then we have the decomposition-based algorithmic solutions to solve the MILP. And we have focused on two methods. So the first one is the optimal approach that allows us to find the optimal solution, but with reduced computational time. And the basic idea here is given by actually bandage decomposition. So it's to take the original problem and split it into two subproblems that are smaller with less constraints and variables, and thus they're easier to solve. So actually, we are splitting the original problem to a master problem and a slave problem, and we are iterating between those two solutions. So the master problem will focus on the frequency to task assignment and the task to process allocation, and the slave problem focuses on the optional subtask adjustment. And as we will see in the next slides, by iterating, we are actually reducing the gap between an upper and a lower bound on our value of the objective function, and thus we are converging to the optimal solution. So this can be seen as a closed loop method. We have also proposed the heuristic approach in order to reduce the computation time. The heuristic approach is based on steps. So first we are doing the frequency to task assignment, then the task to process allocation, and then the task adjustment. So this is an open loop method. So going now a bit into the problem formulation, we have a task model that consists of n independent imprecise computation tasks. So an imprecise computation task is described by this table you can see there. The OI corresponds to the actual execution cycles for the optional subtasks, and this can be between 0 and the capital OI. So when we have 0, it means that the optional subtask is not executed. And OI is the worst case execution cycles that we can have for the optional subtask. MI gives us the mandatory execution cycles for the mandatory subtasks, and then we have the relative deadline per task and the global hyperperiod. Regarding now the energy model, this is given by a multicore platform consisting of M homogeneous processors, and each processor can decide a voltage frequency among these L different pairs that we can have. And the power consumption of a processor at an L level, it is given from the static and dynamic power consumption of the core. So in order to formulate our problem, we have introduced actually 3 variables, 2 binary ones and 1 continuous one. So the first binary is regarding the frequency to task assignment. The second is regarding the task to process allocation, and the continuous variable is connected to the optional subtask adjustment. Regarding the constraints that we need in order to formulate the problem, the first constraint is the task allocation, which tells us that a task should be executed only on a single processor. Then we need the frequency assignment, as expected. This is that each task should be executed with only 1 frequency level. And regarding the real-time constraints, we have 2 parts. The first one says that the execution time of each task should be less than its relative deadline. And the second says that the tasks that are assigned to the same processor should be finished within the global hyperperiod. And the last constraint that we have is regarding the energy consumption. So we're saying that the consumed energy within our hyperperiod cannot exceed the energy supply of the system for this hyperperiod. Now, going to the primal problem formulation, we have inserted a linear function in order to map the relationship between the optional execution cycles and the quality of service. So our goal here is to maximize this function or minimize its negative. So taking this objective plus the constraints that we have discussed before, this is our original problem formulation. So here we can see that the binary variables that I have highlighted in the slide with blue and the continuous variables that are highlighted in red, they are coupled with each other non-linearly. So we are having an MINLP problem formulation. So our next step is to linearize this mixed integer nonlinear programming to our mixed integer linear programming. And this transformation should not change the objective function and the feasible region. Thus, as the optimal objective values will be the same, we can solve the MILP instead of the MNILP. So a bit about the linearization. I will not explain all the maths, just to give you the basic idea. Focused on the variable replacement. So what it says is that we are inserting a set of auxiliary variables to the problem formulation. For instance, here I just have highlighted one. This is an intermediate continuous variable for the task execution time. So with the help of these auxiliary variables, we are creating the linear constraints following this lemma that we have shown that the transformation between the space S1 and S2 is equivalent. So based on this type of transformations, we are able to have an original an MILP that is equivalent to the original mixed integral non-linear program. So going now to the optimal decomposition-based approach. Here, the basic step for solving the mixed integer linear programming is to find the optimal values for the binary variables x. And this is because if we find the optimal values, then the problem is reduced to a linear programming one, which is simpler and easier to solve. So we are based on this idea. And as we said before, this is the main idea also of boundaries decomposition. And we're splitting the original problem into two. The first one is the master problem, which is formulated as an integer linear programming formulation and includes the integer part of the original problem. So these are the binary variables and the corresponding constraints, plus another set of constraints that I will discuss just in a minute. Then in the slave problem, we have the continuous part of our original problem. So here we have the continuous variables and the corresponding constraint. And the idea behind is to iterate between these two problems in order to converge the optimal solution. So in one iteration, we solve the master problem. The obtained value of the objective function gives us a lower bound. And also, as you see with the arrow on the right, we are using the solution to the slave problem. Then we are solving the slave problem with the solution coming from the master. And the value of the objective function gives us an upper bound. Plus, depending on the solution of the slave problem, we are adding a new constraint for the next iteration that we will do. So this constraint can be a feasibility or an infeasibility one. And the goal of adding this constraint is actually to reduce the gap between upper and lower bounds at each iteration. So by iterating with this process, we see that the gap is reduced and finally we're converging towards the optimal. So to give a bit more insight on these additional constraints inserted due to the solution of the slave problem. So if this polytope there shows the domain of the binary variables x, the values that we can have are three. So it's the optimal, it is the non-optimal, and the infeasible ones. So by adding these feasibility constraints, actually what we are doing, we are excluding the non-optimal values for the variables x. And by adding the infeasibility constraints, we are excluding the infeasible values of the binary variable x. So yeah, although with this decomposition-based approach, we are able to reduce the computation time compared when we are solving the problem completely, still we have a computation complexity, and this comes from the solution of the master problem, which is an ILP. Plus the fact that at each iteration, we are adding additional constraints, so the problem is increased. So for that, we have proposed a heuristic approach to have reduced computation time, and we are based actually on a multi-step optimization. So here we're having the frequency to task assignment that happens first, then we have the task to process allocation, and then we have the task adjustment. And the idea in this sequence is to use the solutions of previous steps to the next steps. So semantically, the frequency to task assignment will be used to the task to process allocation and also to the task adjustment aligned with the task to processor allocation solution. So to design our heuristic, we have two key challenges. The one is that the variables should be able to be determined separately. And also when we are obtaining the solutions, a solution coming from a previous step should not be violated at the next step. So I will give a bit more details on the 3 different steps that we have. So what we did at the first step is to consider the frequency to task assignment only for the mandatory tasks. So that means here we are omitting the optional subtask, and we are omitting also the task to process allocation. So we are formulating our problem as an ILP. The objective here that we have is to minimize the energy consumption, and we are taking as constraint, if you remember what we discussed when we were showing the constraints, it is the first constraint for the real time. It is that the task should meet its relative deadline. And in this step, the output is to decide the frequency for the mandatory tasks. So then we are going to the second step. So here we are doing the task to process allocation, again considering only the mandatory tasks. So yeah, we are still omitting the optional subtasks. So our problem formulation is again an ILP, and the goal here is to minimize the task execution time of the processor. And this is, by minimize the task execution time, we are preparing for the next step. So we are creating slack for the execution of the optimal subtasks. So here we have 2 constraints. The first is the hyper period, that all the tasks assigned to a core should meet the hyper period, should not exceed that. Plus, we have the solution regarding the frequency of the mandatory tasks. Thus, we have the execution time of the mandatory tasks. And here we are deciding the task to process allocation. And at the end, we are going to the next step, which is the last one. And this is the decision of the task adjustment. So our problem is formulated as a linear programming. Actually, this part is the same as the slave problem that we have discussed in the beginning. So the goal is to maximize the QoS. And here we have the 2 real-time constraints regarding the relative deadline and the hyperperiod, and our energy supply constraints. Plus the 2 solutions coming from step 1 and step 2. This is the frequency and which core executes which mandatory task. And in this step, we are deciding the task adjustment. So going a bit to some representative results. Here we have the setup. In this setup, we had a multicore of 70 nanometers with 5 levels of voltage and frequency. And we searched for up to 10 number of processors with a step of 2 in the experiments. For the tasks, for the worst case execution cycle of the M and O part, we have randomly selecting within this range, and as the number of tasks has been tuned between 10 and 50 with a step of 10. Regarding the energy constraint, we assume that the system is in the medium level. This means that we do not have enough energy to execute the complete optional subtasks for all the tasks. Otherwise, the solution was obvious. And the energy supply is given by this formula that you can see. The second term is given by the minimum energy to execute M and O and the complete O, the optional part for all tasks. And we are reducing in order to be in the medium level with this energy efficiency factor that is tuned with 0.8, 0.85, and 0.9. So what about the metrics? We compare 2 things. First is the quality of service obtained, and then how much time it took to find the solution. And we are comparing the 2 proposed methods, the optimal and the heuristic, with deterministic approaches. More explicitly was the branch and bound method that can give us optimal solutions for MILP. Stochastic methods, and here we use the genetic algorithm. And to compare with the heuristic, we use this heuristic, the adaptive task allocation. So this is a 2-step heuristic. And the first step, as you see in the slides, it performs the task allocation under satisfying the energy constraint. And in the second step, we are deciding the optional task execution cycles. So this heuristic does not explore the frequency. Okay, so here what we have the QoS for the proposed methods compared with the branch and bound. So on the left, we can see the comparison of the optimal and the heuristic. So overall, the optimal has higher gains, and on average, this is 26%. So these are the box plots for all the n and all the m, so the number of cores and the number of tasks. And the three vertical columns there are the different efficiency factors for the energy. So overall, we see that we are, okay, the heuristic is in average 26% less better than the optimal approach. And then we'll compare the optimal with branch and bound. So here we see that there is no gain. Actually, both approaches arrive to the same solution. Thus, experimentally, we see also that our approach was able to find the optimal solution. Going now to the time. Here you can see on the top of the left is the computation time needed in seconds for the optimal and the heuristic for different efficiency factors. So the curve that you see that goes up, it's the optimal one. For different m's and n's, so overall we see that the execution, the time to converge for the optimal is highly affected by the number of processors and the tasks, but less affected or not affected at all, I would say, with the energy efficiency factor. Whereas the time for the heuristic was not affected by n, m, or e, and it was much more less than the optimal approach. And then we also compare the time for the optimal and branch and bound. And here you see again these box plots for all n and m's. And on average, the proposed approach had 22% more, less time to find the optimal solution. Okay, and the last comparison that we did was with non-optimal approaches. So again, we have the QoS and the computation time. So on the left, we can see the comparison on the first figure of the QoS and on the second regarding the computation time when we compare the optimal approach with the genetic algorithm. So we have some gains regarding the QoS, so 7.6 on average, and around 35.6 on average regarding the computation time. And the last comparison that we did was regarding the heuristic. So we compared our heuristic with theta. So theta is the two-step heuristic. Regarding the QoS, we see that we have a lot of gains regarding the quality, and this is because data does not take into account the frequency assignment. Regarding the execution time, both heuristics have similar results. And also here you can see that sometimes the proposed heuristic may be a bit, may have higher computation time. This is because we are having a three-step heuristic, whereas the eta is a two-step heuristic. So to conclude, we have seen a formulation as a MNILP for the imprecise computation task mapping, taking into account the DVFS for multicore platforms. Our goal was to maximize the QoS, and we had two constraints, the energy supply and the real time. We have proposed a transformation to go from MINLP to MILP, and we have applied two decomposition-based methods, the optimal and the heuristic, that we have seen in the experiments that we achieved reduced computation time. So regarding the extensions of this work, we have the first part on, we have extended this work on heterogeneous platform. And also here, we also took into account the task migration, which has not been taken into account in this work that I have presented. And also in the ZCAS paper, we have proposed a method to accelerate the optimal solution. Plus, we have added tasks with dependencies, because in these slides, we have seen the results and the approach for independent tasks. Okay, that's all from my side. Thank you for your attention.
Thank you, Angeliki. Are there any questions? Yes, Alex.
Yes, I have just two questions. The first one is concern your decomposition. So you compare the result with your decomposition and without?
If we compare the result with decomposition or?
Have you compared the results of the performance of the decomposition scheme against the non-decomposition scheme?
Yeah, the branch and bound was applied in a non-decomposition scheme.
Okay, but when you use your decomposition scheme,
the decomposition. Sorry.
You have decomposed your problem using Bender decomposition. Okay. Your mixed integral linear program. You have decomposed it into a slave or a master.
Mm-hmm.
And have you compared without decomposition, just to see how you gain with your decomposition?
The complete solver that we used for the non-decomposed problem was the branch and bound.
Okay, and have you compared the performance of the two approaches?
Yes, it was the computation time and the QoS, maybe here. Okay, yes, here on the right. I don't know if you see my mouse.
Yes,
but,
yes, you are.
Okay, so this part is about the execution time of the branch and bound, and so this is not decomposed, and this is the one that we did with decomposition.
Okay.
And for the quality, actually the results are the same here.
Okay. So how you gain? What is the factor? Do you have an average factor? Percentage factor of gain? Is the quality of the results equivalent? Yes, it is exact result. So it is the same result for both methods. Only the difference is the time complexity of the algorithm. And
yes.
you can evaluate in average how many you gain.
Yes. So the quality results the same,
mm-hmm.
and the computation time gains on average is 22, as we see in the screen, and this includes the average for all them time. So for all the processors that we have checked and all the task numbers, yeah. So on average is 22, as we see in the graph.
Your result, you get result only on the real cases, or do you try also random generated instances?
Okay. No. It's here we didn't have we have not explored real code. So actually, we are taking randomly the mandatory and the optional, and then this is it's the solving that occurs at design time. So we have not neither as a next step. We have not run code on platforms or on simulation in reality. So this is a theoretical work on.
So everything. So you generated random instances, and but is it really random, or you fix some constraints due to real-time system, for example, particular values of the period, the harmonic periods, or have you tried to?
Okay. So we took the random values based on this range that you see in the slide, and this is given from this citation. So there is an analysis that have been performed in this work. So if I remember well, that was with MeBench and MediaBench benchmarks. So they did several analyses, so they gave these range as execution cycles. So we randomly selected from there.
Okay, so it's really random. You don't try for example, since usually when we consider real-time systems, it's easier when you have some special value of the period, like harmonic or so if you look, for example, this morning we were talking about Rosas, or if you look at this kind of instances, the periods are already very specific, and then the complexity of the problem are usually better, easier, I would say, and it corresponds really to real cases. Even if it is random generated, usually when we look to real cases, we have this kind of value. So usually it's interesting to see this kind of value, since we can get a gap on the time complexity. Really interesting.
Yes, sure. So in this work, we didn't use the more complete task model. So it was instances of one task, and we didn't have multi-periodic tasks or with different periods. But we can extend this by adding offset to the task starting time. So here we do not have that. But when we went to the other works where we use deterministic, not deterministic, dependent tasks, there we have this notion of one task starting before the other because of the dependency. But here the model is more simplistic.
So yes, so you work in your work, the tasks are not dependent, are dependent. No.
Not here, no. This was independent.
And which kind of dependence model do you want to take?
In the work on the dependency, if I remember well, again, the cycles were randomly selected within these rates. And we had also random dependent construction of the graphs. And we also analyzed a bit typical basic kernels like FFT. So we took this kind of structure of dependencies and use it as input. But still, it does not come from a real big application. So
do you, since people doing real-time system usually consider some dependence like let dependence, logical execution time dependence, or there are some dependent scheme working only on the deadlines, for example, that are it will be interesting to see if you can model this kind of dependence using linear equations.
Yes, that can be interesting to extend to more multiple periodic tasks. But that was the first work working with this analysis between imprecise computation tasks and DVFS. So we focused on a simple task model and then tried to formulate this as a first step.
Yes. Thank you.
Thank you. Any other questions? Okay. I have one on my side. Did you try to use usual solvers? Maybe I missed it, to solve your, because you focus here on the presentation on your heuristics, which gave quite good results, but I'm wondering if using like Cplex, Gurobi, or other solvers and compare sometimes the optimal solution obtained within your heuristic to evaluate the gap.
Okay, actually, in the implementation at the end, we did the formulation that to solve the problems, we use MATLAB solvers.
Okay.
And the comparison is as I said, with the branch and bound and the genetic algorithm.
So yeah, just an option, let's say, to try Cplex and Gurobi.
Yes. Okay, this was the as I said before, that is the initial work. So I decided to show that because it was the less complex one regarding the constraints. But in the next works, yes, indeed, we use Gurubi as a solver. So this was based on MATLAB. But, yeah, and we get better results actually because we compared when we changed the solvers. We compared what we took from the MATLAB solver and the Gurubi solver, and the results were much better with Gurubi. So it's the thing to do.
Okay. Well, not surprising.
Yeah.
Thank you very much.
Thank you.